Hello, Chem 212 students, and welcome back. For our next set of lectures, this is going to be on stereoisomerism, which is covered in Chapter 5 of your textbook. Here is a diagram that summarizes what we'll be talking about in this chapter. In general, we discussed the word isomer. An isomer means that you have molecules with the same atoms, but the way their bonding works is different. In the case of constitutional or structural isomers, which we've talked about extensively already, the atoms are bonded in a different way. For example, this fluorine atom is bonded to the first carbon, the carbon on the end of the molecule. However, this fluorine is bonded to the second carbon in the middle of the molecule. And so these would be considered constitutional or structural isomers. In this chapter, we're going to focus on so-called stereoisomers. And in stereoisomers, the atoms that are bonded to one another are the same, unlike in the constitutional isomers, where this fluorine is bonded to a different carbon. Here, all these atoms, the chlorine, the bromine, the fluorine, these are all bonded to the same carbon. So the bonds are to the same atoms. However, their arrangement in three-dimensional space is different, and you can see that here with these 3D models. Okay, and so we're going to talk about these types of isomers now and what this means for a molecule when it has this kind of isomerism. Another type of stereoisomer is a diastereomer. We're going to see that enantiomers have mirror images like we see here. They're mirror images of one another. Diastereomers are isomers that have different arrangements of atoms in three-dimensional space, but they are not mirror images. This includes cis-trans isomers that we have discussed before. It can include conformers and rotamers as well, which we talked about in Chapter 2 and Chapter 4 very extensively. And so let's begin to talk about these various different types of stereoisomers. So first of all, why do you care about stereochemistry? Stereochemistry turns out to be one of the most important topics in biological and pharmaceutical chemistry. And the reason why is that the proteins that do all of the work and are much of the structural material of organisms have a kind of isomerism called, they have stereoisomerism. Specifically, there are many enantiomers of molecules, or mirror images of one another, that are, one is biologically active and the other is not. And so let's say, for example, to dock to a certain protein, another protein or drug molecule needs to have a certain three-dimensional arrangement of atoms in order to have a kind of docking or attachment arrangement to another molecule. If these positions are switched in three-dimensional space, that will result in an inactive type of interaction here. And so that is why when it comes to drugs and biomolecules, often one isomer here, one stereoisomer, will be biologically active or functional, and the other will be completely biologically inactive. Or in some cases of drugs, the other enantiomer or optical isomer, as they're called, will have a negative impact biologically or in terms of health. So that's why this particular topic is so very important. It's important to biochemistry and to drug discovery and purification. So again, we can divide isomers into two large classifications. One is constitutional isomers, in which atoms are bonded to different other atoms. However, the molecule contains all the same atoms, just bonded in a different way. In stereoisomers, all the atoms are bonded to the same other atoms between the two isomers. However, they are arranged in a different way in three-dimensional space. And so you saw a pair of molecules that are constitutional isomers. You saw some examples of that on the first page. You can have stereoisomers in for various different reasons. One of these might be because you have a ring formation, and we mentioned this very briefly in a prior chapter. In the case of a ring, the ring locks the sigma bonds, the single bonds between the carbons, into a particular arrangement so that it can no longer rotate around the single bond as freely. And so what you end up having is what we called cis-trans isomers. Cis, where the atoms are on the same side of the ring, for example, both these methyl groups being on the top, versus trans, where these methyl groups, one is on the what we might call the top of the ring and what we have on the bottom. And so we discussed this briefly, and we did have a naming system for cis and trans, but when things get more complicated, we're going to need an addition to our naming system besides cis and trans, just to differentiate between particular molecules. This will depend on whether or not they have enantiomers, they're so-called chiral or optically active, as we're going to say, or whether or not they don't. So let's go further here. Besides a ring, another situation where you might have stereoisomerism, particularly diastereomers, is when you have a double bond. So both of these situations, the ring of the double bond, result in molecules that have a position that cannot rotate. Single bonds can rotate, but there is some barrier to rotation that we discussed in chapter 4. But these molecules here with a double bond, they cannot rotate around that double bond unless the pi bond is broken. Remember, the pi bond requires a sideways overlap of unhybridized p orbitals, and that overlap is broken if this atom here tries to rotate. Its p orbital will then rotate, but that will require the breaking of this pi bond here, and so that's very energetically unfavorable and tends not to happen at normal temperatures, standard room temperatures and so forth. So let's take a look and see if we can identify these molecules as either the same molecule, constitutional isomers, or stereoisomers. So let's first take a look at molecule number 1 here. This molecule it's a cyclohexane with a alcohol functional group attached. And here it is in the axial position, here it is in the equatorial position, but we know due to the ring flip of a molecule, so if I have this right here, and these kinds of models really help. If you haven't gotten some of these, I do highly recommend it. They're not absolutely necessary, but they do help a lot. They cost about 20 bucks. You can look in the syllabus for recommendations on that. But let's say this is the molecule here that is at the top, and then if I do a chair flip, then suddenly I have the other isomer. So really these are conformers of one another, and so they could be considered stereoisomers. There are, I mean, because they can interconvert, you might also call these identical. There's a very free interconversion between these two, and so that's kind of a gray area in the terminology. We can call these stereoisomers, but really because they can interconvert so freely, we might consider these conformers identical. It's a matter of the barrier to the rotation or the movement of these. When they can freely rotate, their stereoisomerism cannot easily be observed when they can freely interconvert. For number 2, now these are going to be different because we can see that in one of these we have a OH that is in the axial position on the top of the ring, and an OH that's in the equatorial position next to it on the top of the ring. However, in the neighboring structure, we have an axial OH and an axial OH right next to each other. And so this is certainly a different situation. In this case, if we were to draw these as a flat Hayworth type structure, we could say that we could draw them in this way. Oops, let me erase that. I'm just going to cross it out. So we could draw it in this way. We have a hexagon, and so this is something we practiced, prior to the exam and was an important part of the exam. These are both in the upward position, so we could draw these as both wedges right here, and like that, as a Haworth projection. Now in this structure here, you can see that one is up and one is down. And so let's say we drew this one here in the up position with the wedge, and then this next one here would be the dash position down. So these are stereoisomers of one another. They're not the same molecule. They're not constitutional isomers either, because they both have the carbons 1 and 2 here bonding to OH. So they're not constitutional isomers. They are stereoisomers. Their bonding arrangement differs in three-dimensional space. Here we have two molecules that are also stereoisomers of one another. So these ones, we call them identical. There's an argument for calling them stereoisomers depending on the barrier to the interconversion, but that's quite low. Here we would call these stereoisomers. Here, these are also stereoisomers. You can see that the rotation is around this bond here. So if this, obviously this bond can't rotate. So this is a distinct position from the down position. So this is, let's see, I'm going to erase that now. So what we see here on the left side could be referred to as the trans isomer. Since one of these is going up, one is going down, the hydrogens would be right here. So we can see that these larger groups are opposite to one another. So this is what we would be calling the trans isomer. However, here the larger carbon groups, large relative to hydrogen, are on the same side. So we would call this the cis isomer. So this would be considered considered stereoisomers. Again, stereoisomers meaning that all the atoms are bonded in the same way. They're just arranged in three-dimensional space. This carbon is bonded to a hydrogen and a methyl, and this carbon is bonded to a hydrogen and an ethyl. However, the three-dimensional positions of these are different because there cannot be rotation around the carbon-carbon bond. For these here too, this is a completely different bonding arrangement. So these are either completely separate molecules, or they are constitutional isomers. So to figure out their constitutional isomers, we want to count up the carbons. These each have 5 carbons here. Sorry, 4. 1, 2, 3, 4. 4 carbons rather. So 4 carbons here. Here we have 1, 2, 3, 4. 4 carbons. In terms of oxygen, they each have 1 oxygen. And in terms of hydrogens, there would be 2 here, 2 here, 2 here, and 2 here. So that's 8 hydrogens. 8 hydrogens. Let's see how many hydrogens are on this one. There would be 3 at the end here, plus 2 more, that's 5. None here, plus 3 more on this carbon, that's 8. And so C4H8O. These are both C4H8O, and the bonding arrangements are different. So these would be considered constitutional isomers. And then these two molecules here are exactly the same molecule. If you were to take this molecule right here, and I don't have enough room behind my head, but I'll put it here. If you were to flip it, just flip it like a pancake vertically, you would end up with this, which is exactly the same as this. So if we just flip it like a pancake, flip, we can see that this is exactly the same molecule. So this molecules here are identical. And so that's some practical ways of identifying whether you have a stereoisomer or not, or whether you have the same molecule. Again, models really help here. If you're having trouble flipping it in your head like this, you need a model to flip it, to rotate it, so you can see. This can really help. You can also build these in mole view. So let's say I'll discard these for now. Let's say you're in mole view, and you want to see if two molecules like the last one we did. Let's see, let's build that one. So we put a double bond between two carbons like that. We put two methyls right there, and then we put one methyl over here. We tell it to clean it up so it looks nicer. There it is. And then we can do 2D to 3D. And so there's the actual structure. And so you can see that if you build this and you flip it around like that, you get the same structure as the other one. This one's kind of easier to see here. But if you need, if you want to look at these and flip them, but you don't want to just do it in your head, you can always use mole view. I do find it's nice to have a physical manipulative as well. Okay. So when you have rings and carbon-carbon double bonds, you have a cis-trans notation. And we talked about this a little bit in chapter 4. So cis is considered when identical groups are positioned on the same side. Trans is when identical groups are positioned on the opposite side. So that's what we learned in the previous chapter. But what if they're not identical groups? Which is a great question, right? What if cis, in that case, cis and trans is not good enough to identify the difference between these? And so we're going to have another naming system where we designate E and Z, which will allow us to deal with if the situation where these groups, like these methyl groups, are different from one another. Let's say there's a chlorine atom here. How would we handle that? We could maybe still call it trans, although it really only technically applies when you have the same group, although it's often used otherwise. But if you want a better designation, we're going to get to that later. But at the very least, we are picking between two stereoisomers right now. These are stereoisomers of one another, and so the cis and trans designation is used to specify that. So here we can see that if we have two hydrogens, we can still use this cis-trans relationship because we're talking about hydrogens. The issue comes about when you have even another type of group here, right? So here we have two ethyl groups that are trans. So cis and trans covers a lot of situations. But as we're going to see, you could have 4 different groups attached. How are you going to deal with that? We're going to need something that encompasses cis and trans and even allows us to do the same type of analysis for other structures as well that don't necessarily have identical groups positioned on either carbon here. So let's take a look though with cis and trans here. So here for question 1, here we would have hydrogens right here to give these carbons each 4 bonds. So these hydrogens would be on the same side, so same side cis. See, same side cis. Okay, cis. I just remember that because it kind of sounds like same, all right? Cis. In this case, as we described, both of these oxygens are on the up position. Here, the down position would be axial here, but there's a hydrogen there. So these are on the same side, these two OH groups. So we would call this a cis conformation. Now, in the next structure here, we'll have a hydrogen right here and a hydrogen right here. Since the two hydrogens are opposite, we would call that trans. Here we have the OH in the up axial position. Here we have it in the down axial position. And so these are on opposite sides of the ring. This would also be called trans. And then here, this one has neither trans nor cis configuration. Why is that? Well, because here, if we switch these two groups, they're the same, right, on this carbon. So one rule of thumb that you can kind of keep in mind is that if you have a double bond like this and both groups coming off are exactly the same thing, you don't have cis-trans isomers because switching them doesn't make any difference. It's the same molecule. So this would be neither. So beyond the cis-trans isomers, there's a lot of other important stereoisomers. And first, we're going to identify the types of stereoisomers that occur when in chiral molecules. So, and that has to do with mirror images. So a chiral object, and this could be a molecule or it could be lots of other everyday objects. A chiral object is an object that is not the same as its mirror image. So for example, human beings are chiral. They have a left side and a right side that are not the same. We know because if you look at your hands, they're mirror images of one another. But when you try to put them one on top of the other, notice that they're not exactly the same thing. Your thumbs and all your fingers are positioned in a different way in three-dimensional space. And that's because your hand does not have a plane of symmetry anywhere in it. And that's how you can tell a superimposable image versus a non. My coffee cup is not chiral because there's a plane of symmetry right in the middle. And if I had a copy of my coffee cup that was a mirror image, I could put them right on top of each other. The handle would be, I could position the handle the same way because there's a mirror image right down the center of my handle of my coffee cup. However, my hands are not like that. There's no place where you could split the hand in half and it's going to be the same on one side that it is on the other. So we say that chiral objects like your hands are non-superimposable mirror images. So what you can do is you can take a mirror image of an object and see if you can superimpose it on the other. Meaning, if you put one on top of the other, can everything be positioned in the same side? And this is something that applies to molecules. Chiral objects include hands or gloves. Anything without a plane of symmetry in it could be chiral. Sometimes objects with a plane of symmetry are also chiral. That's something we'll talk about as well. They can have a plane of symmetry, yeah, or it could be achiral due to a plane of symmetry. Sorry, I misspoke. So we have to look out for that plane of symmetry. So to correct what I just said, if there's a plane of symmetry, it will not be chiral. And so we'll have ways of looking out for that, and we'll have some shortcuts too. And as I mentioned at the beginning of the chapter, we care about chirality in molecules because the molecules that work in our body depend very much on the chirality and the positioning of all of the parts of that molecule in three-dimensional space. And so drug discovery is defined by a lot of this separation between various enantiomers, meaning two molecules that are non-superimposable mirror images. And so again, as I've mentioned, the handheld models really work, really help, but you could also use MolView and digital versions of models as well. So here, what we've got is a mirror image. So we have the actual molecule structure here, the model, and we can see its mirror image, and that is described by these drawings on the left. So you can see the methyl here. So this left one corresponds to this one here. So the methyl is on a wedge popping out of the page. It's signified by this green atom. The ethyl is signified by the white sphere here. It's going back into the page, and in the plane of the page with the flat lines is the OH here, represented by this red sphere, and the hydrogen represented by this blue sphere. Okay, now the mirror image is right here. And so again, the hydrogen and the OH are in the plane, and the methyl's popping out and the ethyl's in the back. But the thing is that, and I'm going to represent it here, my colors are a bit different, but here's another example, and I'm going to switch to my main camera. So here are two mirror images. However, you're going to see that these are not the same molecule. If I try to superimpose this, so these mirror images, if I try to turn this around so that the orange sphere and the red sphere are lining up, what you'll notice is that the purple sphere and the white sphere are not in the correct position. These are non-superimposable mirror images, just like your hands. So they're mirror images, but when I try to superimpose them, one finger is sticking out in one direction and the other finger is sticking out in the other, and they're not the same. Just like when I do it with my hands. When I take the mirror images and I superimpose them, they're sticking out in the wrong way. And so that is an example of a chiral molecule, and its mirror image that's non-superimposable is referred to as its enantiomer. So first of all, let's try to spot chiral centers. So obviously, trying to construct something like this in your mind and rotate it and visualize it is extremely difficult to do on, without a lot of practice. You can get better at it. You get better and better at it, and really good organic chemists have a very strong ability to rotate a molecule in their mind and visualize it. However, we can use, in the meantime, while we're learning this, and we'll continue to use this, I still use this, I look for chirality centers, or atoms that indicate a chiral molecule. We can identify a chiral center as an atom that has 4 different groups attached to it. So for example, this carbon atom here, represented in green, is a chiral center, because if I draw in the hydrogen here, there's one hydrogen that gives this carbon 4 bonds. The chlorine is popping out of the page, the hydrogen is going back into the page, and then this group is a methyl group here, and this group is an ethyl group here. That's 4 different groups attached. Notice that it's okay that these are both carbons. They're still different because there's another carbon here. So that's 4 different groups. So this carbon is a chiral center, and the way we generally indicate that is we draw a little star. If you're indicating on a piece of paper without color, it's common to draw a little star next to the chiral carbons, if that's what you're analyzing. Here's another example. Again, there's a hydrogen that's on the dashed line here, and there are 4 different groups attached. The OH, the hydrogen here, then there's an ethyl group with 2 carbons, and then there's a propyl group with 3. So that is 4 different groups, and so this is a chiral carbon right here. And then with rings, this is a little bit different, but again, we've got to have 4 bonds, so there is a hydrogen attached here. It's on the dash but not drawn. And although both of these groups are connected to the ring is not the same all the way around. The ring going to the right side has a double bond. However, the ring going to the left side does not have a double bond in the same position. So this would also be considered 4 different groups. Now this is as opposed to the situation where if we had bromine on the wedge here and there was no double bonds, well then in that situation the left side and the right side would be considered the same and not different from one another. So this here is chiral and this one is not chiral. And the difference is the fact that there's a double bond here, making this group branching from the right different from the group branching to the left. So identify all the chirality centers in the following molecules, and I will remind you on any of these, when I do these, if you're feeling confident, and even if you're not, I'd say pause the video, give them a try. Every time I show you some example problems like that, pause the video, give it a try. See if you can figure it out yourself. So pause it now if you want to. Okay, now I'm going to give you the answers. So here again, we're looking for a situation where we have a carbon with 4 different groups attached. Now, these carbons here, these are not chiral. So the reason why is because each of them has 2 hydrogens attached, and the hydrogens are the same. If there was another atom attached, then this going in this direction would be different than going in this direction, and so you'd have 4 different groups. However, here we have this carbon has an OH and a hydrogen attached, but if we go around the ring each direction from this carbon here, it's exactly the same in both directions. So this molecule is not chiral. There's no chiral centers here. Okay. Now that is different from this situation. So in the situation on the right here, we have hydrogens attached. And so each of these four directions will be different. Each of these here would be a chiral center. Now I will say that there are, to determine if the entire molecule is chiral, it is possible to have chiral centers, but an achiral molecule, if there is a plane of symmetry somewhere in the molecule, and there would be here, this is going to be what we will refer to as a meso compound. So there are chiral centers. I've indicated them here, but it's going to turn out that the molecule as a whole will not be chiral for reasons that we'll discuss later. Now let's look at this one here. Well, let's fill in some hydrogens. So there's a hydrogen on the dash here. There's 3 hydrogens here. Here there's a hydrogen on the wedge. And here there's a hydrogen on the dash because the other one's the wedge. So this carbon is not chiral because there are 3 hydrogens attached. This carbon is not chiral because there's 2 hydrogens attached, which are the same. And this carbon is not chiral because there's 3 hydrogens attached. So our chiral centers are right here, right here, right here. And this is because if you go in one direction, yeah, it's carbon, same as here, here, or here. Actually, and let me correct myself here. This carbon here is not chiral. I just noticed. Why is that? Well, it's because this group right here, this methyl, is the same as this one. So this carbon, in fact, does not have 4 different groups attached. These methyls are the same type of group. However, this carbon here is chiral because this group on the left is different from this group on the right, which is different from hydrogen, which is different from methyl. Same thing on this carbon. This group on the left, all of this is different from the ethyl group on the right, which is different from methyl, which is different from hydrogen. So there are 2 chiral centers. This carbon is not a chiral center because of the 2 methyl groups. Okay, now let's identify some more chiral centers. So remember, a chiral center has to have 4 different groups attached. So any of these sp2 hybridized carbons with a double bond here cannot be chiral carbons. These carbons on the end here are not chiral because they have 3 hydrogen atoms attached. This carbon is not either. Neither is this one because they both have 3 carbons, 3 hydrogens attached. And this one here has 2 hydrogens attached, right here and here. So none of these are chiral. So this one may be chiral though, and this one may be chiral. Let's make sure. We can draw in the hydrogens. So the hydrogens here are on the dash, since the wedge is the ethyl group there, and this hydrogen is on the wedge. So if we look at the 4 groups here, this is a methyl group, this is a hydrogen, this is an ethyl group with 2 carbons, and then there's this one, which is all the rest of the molecule. So this is a chiral carbon, 4 different substituents attached. This carbon here has a methyl group, a hydrogen, then this group on the right is different from this group on the left. So these are the 2 chiral carbons here. So some stereoisomers can be classified as enantiomers. Those are the ones that have non-superimposable mirror images. So when you're drawing a mirror image, there's a couple of ways you can do this. And again, the handheld models help to solidify this idea. But if you're drawing the mirror image, you can simply draw the same thing you see, but flipped on the mirror plane vertically. So it would look like this. Now there is another way to do this that is simpler. If you have just one chiral center, and in this molecule, or for each chiral center rather, you can do this if you have more than one as well. But for each chiral center, if you flip the wedge and dash positions, or flip any of the 2 positions, you can also get the enantiomer. So for example, here I could draw the enantiomer with a dash for the chlorine instead of the wedge, and then as long as the rest is kept in place, that is also the enantiomer. How do I know that? Well, if I take that molecule and I flip it like this, I will get this one right here. The chlorine, if I flip it like a pancake, the chlorine will be sticking out, and also this ethyl group will be pointing to the left and the methyl to the right. So there are two main ways to draw the enantiomer easily. One is to make a mirror plane and just mirror everything like I did here. So the ethyl is closest to the mirror plane right here. This is the carbon. The chlorine is all still wedged because it's a mirror. It's still coming out towards us, and then the ethyl is out in the back furthest away from the mirror. Or you can, to draw the enantiomer, you can invert the positions on every chiral carbon, and you'll also get the enantiomer. So here are two very common examples for molecules that are enantiomers of one another. R-carvone and S-carvone. And so notice this designation, R and S. This is going to be the way that we designate two enantiomers of one another. And for each chiral carbon, we'll have to state whether it has an R or S designation. In this molecule, there's only a single chiral carbon. That's the one right here. That's the only one that is attached to 4 separate groups. Because these ones are on the double bond, this one's on a double bond. So the only other possibilities are these two here, but these both have 2 hydrogens. So these cannot be chiral carbons. So there's only one chiral carbon, and this chiral carbon here is going to have the so-called R designation. This one will have the so-called S designation. And you can differentiate them based on the dash and the wedge. So another important idea here is, you're not going to be able to tell whether it's RS without the dash or the wedge, or whether it's one enantiomer or the other. Notice that these two have different odors, and you're actually going to smell these in lab later on. And but otherwise, they have identical physical properties, and that's going to be an issue with enantiomers that we're going to talk about. There's only a limited number of properties that you can use to differentiate from them between one another, unlike other isomers that we have seen that have different boiling points or melting points. Two enantiomers, as we're going to see, are going to have the same boiling and melting points, and so this means that separating them becomes extremely difficult, which is one of the main challenges of pharmaceutical chemistry. So it's important, because enantiomers are not identical, we must be able to give them different names. And the way that we're going to do this is we're going to use the so-called Kahn-Ingold prelog system. And we're going to be designating carbon atoms as R or S, or each chiral center we're going to designate as R or S. And so that's what I'm going to begin to get into in our next video. So I'll see you then.